determine whether each of these are classification or regression. If so, explain why. Also provide the possible inputs as well as the possible outputs, so like the labels and categories. So let's start with the first one. What type of problem is predicting the future's stock prices? Yes?
Regression.
Yes, that's precisely right. And can you provide me the possible inputs or justify why it's regression?
Like if it's like a set of numbers and they're like increasing, then there's a chance that they're going to increase. But the future, like you can draw a line for that.
Yeah, continuous real values. How about email spam detection? What do you guys think email spam detection is in terms of the problem we're trying to solve? Yes?
Classification, like, you know, it's either spam or not spam.
Yep. And what type of possible inputs?
Probably just the email text plus, you know, maybe some information on sender and title and such.
Yep, that's precisely right. How about a malignant tumor detection? What do you guys think this type of problem is? You're trying to fix.
Classification.
Yes.
This is like based on different manual images that you provide to feed to the machine. Like,
That's precisely right. And what type of possible labels or categories do you think might be in the range space of it?
size, diameter, I'm not sure what the malignant means. What does it
It's like a deadly tumor.
that
It means deadly tumor. So it could be malignant or not. Yeah, malignant or not
Yeah.
malignant. This one is a little bit more ambiguous, and I actually put it here on purpose. So what about weather forecasting? Yes?
I'd say this is a regression. Just, you know, like the outputs, like you would want to measure one specific aspect of the weather at a time, temperature or humidity or wind speed or whatever. And then, so that would be your output, some number representing that, and then your input would be all the fluid dynamics and atmospheric data that you've gathered over the last.
You're right. It could be a regression problem, but it could also be a classification problem in the sense that you're trying to predict whether the weather the next day would be sunny, rainy, or cloudy, correct? How about, and this one's a little bit trickier, and you kind of need to think about it a bit deeper. Written number recognizer. So essentially you can predict decimal numbers, 1 billion, 1 trillion. So what type of problem is this? Yes?
You could say it's a classification problem because technically you can classify numbers
Yeah.
in different sets, like real numbers, rational numbers, complex numbers, irrational numbers, test numbers.
Sorry, I wasn't being clear. Like, based on written numbers, you try to predict what exactly the number is. Not what type of number. Yes?
Isn't this a series of classification?
Yes, it is a classification problem in which your range space is basically infinite. The reason why it's not regression is because based on your output, the numbers are not really ordered in any way. You're just classifying what number it is. And what is the possible labels or categories of this? Yes? I said including decimal numbers.
Yeah.
Yes?
sorry, I think for the image recognition, when you write things on a paper, like you kind of like in the computer, it's actually a matrix, right? Like black, white, and when there are numbers, it's black. Like
Yeah. That's exactly what it is.
The 2 is actually 0, 1, 0, 0, 0. Black is 1, 1. So the ink is 1. The white space is 0, and there are some colors. I'm not sure, but maybe.
Well,
I don't
the
know.
answer to this would be basically every rational number, because you can represent every rational number as a finite decimal number. And how about, this one's a little bit more tricky. If you don't know what reinforcement learning is, then this might be a bit harder. So what do you think is training a robot to traverse a maze a classification or a regression problem?
Something you can do is if you have categorical data,
Yes.
that can be easily, so if you tell the robot that if you have any sort of categorical data, you use classification, because categorical data is technically, like classification is way better for treating categorical data
Yeah.
than regression is. So one way of doing that would be like can the data convert if it's discrete data or categorical data, and depending on that, compare.
Sure, if you put it that way, sure. But in general, this is actually neither classification nor regression. As I said, this is related to reinforcement learning, which is essentially something, it's really complicated. I'm not going to go in depth to it. I don't think this bootcamp is going to go in depth into reinforcement learning. But essentially what it is that if the model does something wrong, we basically beat it with a stick, we punish it. If it does something right, we reward it, all right? Is everyone good with? So in classification analysis, there are 4 main categories we're going to be talking about. The first one might be a little bit deceiving because it has the word regression in it, but in reality, it is a method of classification. The second one, I've probably shown you it in the first slide, but it's called k-nearest neighbors, which is essentially, it's as it sounds. You take the k-nearest neighbors, and based on the majority, and it basically predicts the labels on the majority vote of what the categories are of the k-nearest neighbors. And the third one is decision trees. Also as shown in the first slide, decision trees basically partitions your data space into multiple subspaces. And random forest classification just adds a little bit of randomness to the decision tree and combines all, like a bunch of decision trees to one. So let's start off with talking about logistic regression. Logistic regression predicts a categorical dependent variable from a number of different independent variables, and this is usually used for binary classification. So right here, I have an image of linear regression on one side and logistic regression on the other side. So can anybody tell me, like, what's the visible difference in the images?
So the red line one is linear, the other is like so you may call it like a sigmoid.
Yes, that's exactly what it's called.
Arrow function.
Yes. So in linear regression, when we're trying to predict based on our data, we're predicting based on a trend, and we're trying to draw a trend line through our data, or a trend curve. However, with logistic regression, it's a little bit more weird. Right here, we have all these data categorized as zeros, and data up here categorized as 1. And you can also notice that we also have a threshold value. And what this curve represents is a probability curve, and as he said, it's known as a sigmoid curve. So how this works is that when you plug in a value into this function, if a value falls below the threshold line, then it will be categorized as 0. Otherwise, it will be categorized as 1. So a basic intuition of logistic regression. Does anyone not understand this notation just before I start? Does anyone not understand this notation? Okay, I'm assuming everyone understands this notation. So basically, this disgusting looking function here represents like a multivariate sigmoid function. The B naught value represents how much you want to shift the sigmoid function left or right, okay? And all of these terms here, if you fix, like let's say we fix every term except for B1, X1, then what we're doing is that in each dimension we're getting this sigmoid function right here for each dimension. And what the beta term does is that it scales it. It scales it in a way such that it compresses it or it elongates it. And essentially to optimize this sigmoid function, it's actually extremely complicated because it uses topics from information theory, in which is taught in 30. So I would not go over how to optimize it. But essentially the whole idea is that you use the method of maximum likelihood. And this is the formula for the maximum likelihood. You take the probability of passing. So to calculate the probability of passing, what we do is that we take the data points, get its corresponding features, and map it to the sigmoid curve. And we basically product all of that together. To get the probability of failing, we do the same thing, but for all the failing values. But we take 1 minus that, and we product all that together. Take that, and that multiply it with the passings, and that's how you get the likelihood. And what we're trying to essentially do with the likelihood is that we want to maximize the likelihood using very advanced gradient techniques, which I will not go over in this bootcamp. And as he said, the sigmoid function, the function g is known as the sigmoid function, and it represents a probability. So basically our output space for our logistic regression. we are essentially calculating the probability of a label occurring, provided that we know the parameters of B. So the reason why, okay, let me go back to this slide. Oops. Sorry. So basically how the likelihood works is that we're assuming that we already know the parameters beta, and we're trying to fix it so that we have this curve here. But there's like infinitely many different betas we can choose from. And that's the reason why we have to use gradient techniques in order to solve this type of problem. And taking, sorry, if you don't know what a gradient is, basically taking like the partial derivative with respect to each variable, beta 0, beta 1, beta 2, beta 3, etc., etc. Sorry, my throat is getting really dry right now. So, in general, to evaluate your classification, well, sorry, give me 1 second. Thank you, thank you. Okay, so to evaluate your classification models, you would use what is known as confusion matrix. Step 1 is to split your data using a rule of thumb of 80-20 into a training set and a test set. So what you're doing is that, because you know you have your data as like a bunch of rows, right? So you want to take all those rows, 80% of those rows as your training set, and only 20% of those rows as your test set. And we use the training set to train our model and use that model on our test set to evaluate it. As for the confusion matrix, here are the confusion matrices, and they are basically, there's 2 cases to it. The first case is that we have a binary confusion matrix. So right here, let's assume a situation that we're trying to predict whether a flu shot or the coronavirus is actually works properly. So let's say we tested on a person and he gets positive, but in reality, they're actually positive. That's exactly what we want. That's known as a true positive. Let's say we tested the flu shot, the corona shot on a person and they receive negative, so they're not. So we think that they don't have corona, but in reality, they do have corona. That's also what we want. That's called a true negative. Now, you can clearly see that the cases on the diagonals are exactly what we want, but the cases on the off diagonals, let's take a closer look at it. What if we got positive, we predicted positive, but then the person doesn't have corona? We do not want that. Even though it's not really big of a deal, we say they have corona, but they don't actually have corona. It might cause them a little bit of trauma, but it's not really a big of a deal. However, if we say that they don't have corona, we predict that they don't have corona, but in reality they do, that could be a huge detriment. So in this situation, we want more false positives than false negatives. And to calculate the accuracy, as you might have guessed, we take the sum of the diagonal, all the cases that we want, the true positive, the true negative, and divide it by the total. So everything in the matrix. And we can generalize this for basically n dimensions. So in this case, here's an example. You want, let's say you predicted Setosa, then you want the actual value to be a Setosa. Let's say you predicted versicolor, and you actually get that the flower is a versicolor flower. How about Virginica? Then you want to predict that it's a Virginica, and you actually get it's a Virginica. That's exactly what you want. However, everything else in the off diagonal is like a mismatch, so you predicted incorrectly. And to calculate the accuracy of your model, we calculate the accuracy of the multiplex, which is the sum of the diagonal, as well as everything in the off diagonal. So let's code up logistic regression. All right. So open up. Is everyone here in the Discord? Yep. Who's not? You're not in the Discord?
Yeah.
Can you sign in the Discord? So open up the Discord, go to resources, and download the breast cancer data set. Sorry, did the previous slide make sense to everybody? Was anything confusing for anybody in the previous slide? Yep, so just download the CSV file and import it into your collab. Name the collab week 4 classification. Who hasn't imported the data set yet? Good. All right, perfect. So, what you want to do first is, because if you open up the data set, we can clearly see there's a lot of columns that we have to deal with. And unfortunately, that means we're not necessarily able to graph it out, because if we were to graph it out, it would be like more than 3 dimensions clearly. So that's a huge problem when you're doing like machine learning and whatnot. So unfortunately, we're not able to print out the data. So first, you want to import pandas as PD. You want to import NumPy and ND, and that's about it for the imports. You want to run this so that you don't forget to run it. Now, you want to create your data frame. Okay. Let me see. You want to import your data frame, and to do that, you do pd.read CSV, and the name of the CSV file, which is breastcancer.csv. All right. After that, you want to take a look at our data set. To take a look at our data set, let's say we want to get the first 9 rows of our data set. So do df.head at 9. And let's see what happens if we run it. Good. Once you have this, I need you guys' help here. Which columns do you think, like even though you don't know anything in medical, which columns do you think is clearly unnecessary for this? Like it has no correlations to any of the data within our analysis. Which column? Yes, exactly. So when we're extracting our feature variables, we want to omit the column of sample from them. All right? Next step, we want to store our independent and dependent variables. We do that by using ilog, df.ilog. So in this ilog parameter, when we do, it's separated by a comma, but when we do colon here, what it does is that it basically takes every single column in the space. Sorry, not columns, but every single row in the space. But then since we want, starting from this column, remember code starts at 0. So this is the 0th column, this is the first column, and in Python we call this -1. So we do the following. Take from the first column all the way up to the last column. And then we do the same thing for our dependent variables. Is everything better now?
You can close the sides.
All right. So I need you guys' help here. What goes in between the square brackets? What do you guys think will go in between these square brackets, based on what I've told you about the format, the bylog, and the previous? You want to give it a try before I move on? Is it someone can tell me? Remember, when we do colon, we take every single row. This side of the colon corresponds to basically the rows, and this side, the other side, here, corresponds to the columns. And as for why, we want to predict the classes. Yes. Yes. Colon, comma, -1. Correct? And why is that the case? Because when we do colon, we take every single row and split it by the comma, and then we take the last column. That's what we want. All right. So, luckily for us, when we're trying to split the data 80-20, scikit-learn actually does it for us. And scikit-learn is a library in Python if you haven't known by now. So what you want to do is that you want to, let me comment this real quick, 80-20 split. So from scikit-learn dot model selection, import what is known as train test split. Okay. Train test split is essentially a library inside of scikit-learn dot model selection. Okay. And then what we want to do is that I'll do the following and I'll explain later. X test, Y train, Y test. And that's equal to, we're going to use the train split test, train test split from scikit-learn. And the parameters for this function are X and Y, which are your independent and dependent variables. The next parameter is the test size. So, like I said, you want to do a 80-20 split. So, you want it to be 20% test sets. So, we specify this as 0.2. And as for the random state, just so that everyone has the same answer at the end, just set it to 0. Okay? Just give me this a second. All right. After that, we want to import. We want to actually use the logistic regression model. And to do that, we can import the logistic regression model from scikit-learn. From scikit-learn.linear model, import logistic regression library. Okay. From there, we want to train logistic regression model. To that, we set the variable classifier is equal to the logistic regression model with random state 0 so that everyone gets the same answer at the end. And then what we want to do is that we want to train it. And to train it, we do the following. Classifier dot fit X train and Y train. Because you want to use the train set, the X variables for the train set and the Y variables for the train set in order to train our logistic regression model. And in the background, it does all the maximum likelihoods, all the gradient stuff in the background, so we don't have to do it. Just give me a scroll. After that, you want to predict the values of our test sets, yes?
What is random state 0?
Random state 0 is essentially it's fixing it. It basically like let me scroll up. So what it does is that because when you set a random state not equal to 0, it basically randomly picks. It basically randomly picks our roles to split the data set, and we don't want that because we want everyone to have basically the same prediction at the end. So we're basically fixing random state to be 0. After that, what you want to do is that you want to use your model to predict values from our test set. So that's why we have our test set. We use our model to predict values from our test set. Okay. Predictions on test set. Call it Y pred. Is a classifier predict X test. Oh, sorry, we need to run all these boxes so that it doesn't give us any errors as such. There you go. Okay. Now, you don't have to know what this does, just copy it and you'll see what it does. So np.concatenate. So basically what we want to do is that we want to compare our predictions with the actual values, all right? So what we do is that we want to print np.concatenate with the following two parameters, this tuple and 1. And in this tuple, we want to do y underscore pred that reshape. Like your y pred. And essentially what this does is that it reshapes your y pred into basically a column vector, right? So a column vector that is like length y pred by 1, okay? And then the next parameter after that, you do the same thing for your y test because you want to compare your y pred to your y test. So it's basically like copy and paste, reshape. You want to reshape it, not shape it. So make sure you fix that. One. Let me separate it out like this so it makes more sense. Okay. Yes? Yeah, it essentially concatenates it, and one represents like, if you have like 0, I think it does it with respect to the x-axis, but if you want to concatenate like as a column, you're taking the vector corresponding to y pred, and the actual y, you're concatenating them together, get a multi column, so you can compare the values. So let's see what happens when we print it out. I can't spell concatenate. There you go. So as you can see here, we basically combine our y pred, which is the left column, and our y test, which is the right column. And it seems pretty good, right? All these values match up almost perfect. And I think there's probably like 7 mismatches. So in the next line of code, we'll see what the mismatches are. Just give me a second. To find the mismatches, we'll use the confusion matrix that we've used in the previous slide. And to do that, let's call it model evaluation. And for model evaluation, you want to do from scikit-learn.metrics import, we'll import the confusion matrix, as well as the accuracy score. So it calculates the accuracy score for us based on the confusion matrix. As for our confusion matrix, it's pretty simple to implement. It's just a confusion matrix. We call it this. We call it CM equals confusion matrix. And then you want to put your y test and y pred in there because you're basically comparing your y test and your y pred, if you remember the layout of the confusion matrix. And finally, let's print it out first before we go into the others. So right here, you can clearly see that we have 85 true positive and 84 true positives and 47 negative, true negatives. And everything on the off diagonal is basically an incorrect prediction. So how do we exactly predict, how do we exactly evaluate it? We calculate the accuracy. Based on our y test and our y pred. Let's print it out once again. And as you can see here, our model has an accuracy of 0.95, which is, if you multiply that by 100, that's like 95.62%, which is extremely good. All right, that's enough for the coding for logistic regression for now. Let's move back to the slides. So let's talk about k-nearest neighbors. To introduce you guys to k-nearest neighbors, I'll have you guys do this for 5 minutes. I want you to think about what's the optimal way of drawing the decision boundaries overfitting. Because that blue dot is like noise, right? It's random, it's just there. We don't want it to classify that blue dot as a blue dot. So essentially, what happens when k is too small? The model overfits. Why? Because it basically finds its, can anyone explain why it overfits? Does anyone know why? Yes.
I mean, if the only point it takes into consideration is the very nearest neighbor, it has no way of distinguishing signal from noise.
Yes, and So that's why that blue region right here is a blue region in a yellow region. And to counteract the overfitting and underfitting, we do something that is known as feature scaling, which is when you take each column, each of your feature columns, right? So like your height, your weight, and you scale it to the same metric. The reason why we do feature scaling is that if we don't do feature scaling, it can be very detrimental and drastically affect our L2 metric. So let me try to draw like an example here. Actually, no, I can explain it first. Let's say we had weights in pounds and trying to measure like what the gender of the person is or something. Let's say you have weights that have like a median value, like a average value of like, I don't know, 150, right, in pounds. And your height is like meters. So the average value is like 1.5. Clearly the weights have higher value, like has a higher threshold than your height. So when you do the L2 metric, what it does is that it has more priorities on the weights than the height. And that's very problematic. So there's two ways of feature scaling to counteract this. The first way is known as standardization. And basically what standardization does is that it takes each column, it takes each feature column, so like your weight, your height. So it tracks this column, each entry in the column, by the mean of the column, and divide all of it by the standard deviation of the column. And what it does is that it centers your data, it centers your features, each feature, to 0. And the standard deviation just basically represents how much your data is spread out. So the higher your standard deviation, the more spread out it is. The smaller the standard deviation, the more squished it is. So think about like a bell curve, centered at 0. Centered at 0. For normalization, it's fairly straightforward. We take each column, subtract it by the minimum, and divide it by the maximum of the column minus the minimum. And what it does, it brings all the values in between the intervals of 0 and 1. So how do you know which one to choose? It really depends on the situation of the overfitting. And that's something you have to decide as a machine learning engineer when you're figuring out how to solve the problem. And all right, I think we've reached our 1 hour mark. And let's take a break.
Can you stand over there?
Yes. I wonder which one has a working course like that.
Management's like
Huh?
management's
It's a very absolute statement for a very non-specific question. Probably not here. I have to go and do some work, and I have to do a quiz too. Wait, so, oh yeah, that's right, we booked this room, I forgot.
There's also more technical job.
You good?
Let me see what this is.
I have what? Would you like to get started?
Hello, everybody. I'm about to start.
And I have one more. And then also have the
That's everybody. I might be missing So, is everybody ready to start coding? Because I still see some of you guys eating. Who's not ready to code? I'm guessing everyone's ready. All right, perfect. So let's start coding up k nearest neighbors. Let's go back to the same collab. And let's create another coding section. All right. In this coding section, notice that. Let me close this really quickly because this is very annoying. Notice that we didn't really make any modifications to x. We're really only using x to store something in like a variable like x train and whatnot. And likewise, we didn't make any modifications to x train, x test, y test, and etc. So what we can do is that we can use these same variables to basically do k nearest neighbors. And we can do that because I've actually tested out in like another thing, and it gives us basically the same answers. All right, to start with k nearest neighbors, call it k nearest neighbors. And what you want to do is that you want to import the k nearest neighbors library. So give me a second. So from sklearn dot neighbors. Sorry, give me. I need to. You want to import k neighbors classifier. Then you want to train the KNN model, and we can do that because basically none of our training data or training sets have been modified whatsoever. So we're basically working with the same breast cancer set. All right. So we do the same thing. Okay. Classifier. And now recall that I mentioned something about a hyperparameter in which you have to pick yourself. So in this case, we can pick our hyperparameter as n neighbors, and can someone pick like a number? Pick a k number.
17.
17? Okay.
How big for a data set?
Sorry?
How big for a data set?
I have no idea. I have no idea how big it is. I think there's like around 800 entries from what I remember. I don't know, let me see. Oh, it's pretty big. Oh, there's 683 entries. So what you can do is that you can take the square root of that.
26.
Okay, 26. All right. So let's pick our k nearest neighbors to be 26. The metric that I was talking about, we want to use the distance metric, not Minkowski, but we want to use Euclidean metric. And T2 is just represented, because we had like L2, right? The L2 stuff is something in a math field known as functional analysis, which I'll absolutely not talk about because it's a grad topic. But essentially, there's this thing called LP. And L2 is like a generalization of LP. Sorry, LP is a generalization of L2. So with LP, you have like the pth root, and then instead of squaring each distance, you raise it to the p power, which is, for now, it's just not relevant for this case. So just keep it at p equals 2. And finally, train your classifier, you do classifier.fit x train and y train. All right, everything runs perfectly. Now, what we can do now is we can do the following. We can do feature scaling because we want to reduce the amount of overfitting and underfitting. So, and to do feature scaling, lucky for us, scikit-learn does all the feature scaling for us. So to implement the tools, we do scikit-learn pre-processing. We want to import the standard scalar. So in this case, we're using standardization. Standard scalar. SE equals standard scalar to initialize it. So let me make this more clear. Standardization. And now we want to modify our X train. X train, so sc.fit underscore transform X train. And now the next line is a little bit weird. I'll explain why is it like this later. So we do X test equals sc.fit not actually fitting the scalar onto the x test because we use the x train to get our scalar, and then we're using that scalar from the x train on these test set. All right? And that runs perfect. So let's see our values of x test and x train to see what we have. Yep, exactly what we want. Everything's of the same scale. Let's try x test as well. Basically the same thing. And now finally, we want to predict and evaluate our model. So let's do predictions on test set. Set our y predict into classifier predict x test. Then we want to compare our predicted values to our actual values. So we basically do the same thing, np dot concatenate. Make sure you don't mess it up. Np dot concatenate. The last parameter is 2. The first parameter would be basically our columns that we had before. So y pred dot reshape length y pred x dimension of 1 because we want it as a column vector. Our second entry would be y test of reshape length y test. Oh. And we basically get the same thing. And finally, we want to evaluate our model. Model evaluation. From sklearn, you want to, from sklearn.metric, you want to import confusion matrix as usual, as well as your accuracy score. And for the confusion matrix, we do CM equals, define CM as confusion matrix. And it's confusion matrix of your y test and your y pred. I'll print this out to see it. In this case, it will be pretty much a different result. So our choice of k was actually pretty bad. Yeah. So this is actually really, really bad because we want, because this is like 0, this is like 0, this is 0, this is 87, but we have this big number right here. Okay? So maybe our choice of k wasn't as good as we thought it would be. And right here, we want to, unfortunately, calculate our accuracy. What? Yep, our model's pretty bad with our choice of k. So what if we reduce our k downwards? Let's say it's 5. Let's run each one of these cells to see what happens. And we have to run each cell, maybe except for these. Run them. So just run each cell so that everything gets restored. So as you can see here, it's a little bit better, right? You can see like, it's actually matching this time, which is a good thing. That's what we want, okay? Now when you evaluate it, it's good. We get exactly what we want. All right, and that's it for K and N. Yes, K and N. And now, if I can find my mouse. Let's talk about the next topic of decision trees. So a decision tree is another type of non-parametric machine learning algorithm. So the type of splits we're going to be doing with decision trees is called a univariate split, which is basically a multivariate split would be like a split based on multiple dimensions. In this case, we're splitting it one dimension at a time. You see this right now? We start with this. We split it one dimension at a time. And what it does is partitions our space into 2 subspaces. And within these subspaces, it's like a binary tree, okay? It's like a binary tree. We split these even further. And these splits are known as decision stumps, which partitions our data at each step into two subgroups as I said. Classification can, what this diagram represents is like, if the, I think that's width. If the width of an orange is greater than 6.5, then it goes to the left tree. If it's not, then it goes to the right tree. As you can see here, it gets partitioned even more. Height greater than 9.5. So let's see. I can't point to it, but you can see if the height is greater than 9.5, we classify it as a lemon. Otherwise, if it's lower or equal to 9.5, we classify it as an orange. And we do the same thing for the right tree. If the height is greater than 0.6, it's a lemon. If the height, if the height is less than, it's an orange. Pretty basic, right? Does anyone have any questions about decision trees? No questions? Perfect. All right. So, my challenge for you is, can you determine all the possible locations? So, when I say locations, sorry, all the possible locations of the decision stumps. And when I say locations, I mean like, in between which point, it doesn't have to, because there's like infinitely many ways you can place like the lines, right? Like in between which lines. So I'll let you think about this for a second. Or actually, does anyone have the answer? So how many, the question is, it says what are all the possible locations, but the question is, how many possible decision stumps are there? Remember, you can partition it with respect to the y-axis as well as the x-axis. If anyone has the answer, just raise your hand up. Yes?
I mean, if you're doing this with like reckless disregard for what's actually correct, I think.
1, 2, 3. It's actually 8, and you'll see why. So let's first partition it by the x-axis. We get 1, 2, 3, 4 possible splits. Yeah.
There are two splits that are
On the other side?
here. Yeah.
Well, they're like on these sides.
Yeah.
Well, we don't count those because those are like, sorry, we don't count those because those are pretty much useless. If we actually get a situation in that case, I think that's like the worst case possible in terms of finding splits, and that's when we backtrack our tree. Because at that point, that's not a meaningful split, and we'll talk about that, and I'll talk about that a bit later. And finally, we can consider the y splits. Okay, 1, 2, 3, 4 as well. So we have in total 8 possible different splits. So in general, how can we generalize this? Oh, I probably shouldn't. Sorry, I probably shouldn't show that slide. So in general, how can we generalize the amount of splits of our data for like n features? Does anyone know? So for in this case, it's like if we have n distinct data points in like arbitrary. Let's keep it with R2 for a second. If we have like n data points in R2, how many possible splits are there?
2n minus 1.
2n minus
1.
Yeah, it'll just be. I think you're actually writing the slides wrong. Yeah.
Yeah, it should be page
Yeah.
9.
Yeah. Essentially, what he said is correct. And checking for the ideal split is very expensive, as you can see, because if we increase the dimension, as you can see, it's by an exponentiation. So the more we increase our dimension, this number grows exponentially, which is very, very, very bad. Okay. So to counteract this, we do something known as the greedy algorithm, which is NPR. So essentially, the greedy algorithm is that. Let me just explain it really quickly. For each feature, and then for each possible splits, starting at this threshold, we compute the information gain. Nj represents the number of points at node j. And basically, we're splitting it through the t function. And the t function would be like x less than 5, etc., etc. So what is information gain? It's actually a topic in information theory. I was told by my higher-ups not to go into information theory because it's a very complicated subject. But you can think of it as like the best case possible is that when you split DJ, it puts all the classes, so like all the oranges into the DL, but all the lemons in the DR. That's the ideal case. Can you visualize that? Right? When we draw the line, it perfectly separates our data. The worst case is when we split all the DJs into a single node, and like she said, let me go back to this. That will be the equivalent of drawing the line right here. Did that provide us any information? No, it doesn't provide us any information, so we lose our information. Essentially, what this algorithm does, it maximizes our information. It finds the split that maximizes the information. And basically, the last line is just checking if our nj is too small, we can just stop, or nj is equal to 1. Then we obviously have to stop because splitting anymore wouldn't make any sense. And luckily for us, we don't have to implement the greedy algorithm. Scikit-learn does it for us. And finally, let's talk about random forest classification, which is going to be the last thing we're going to talk about. It's really brief. So random forest classification is a type of ensemble learning that combines multiple decision trees in order to create a more robust model. So what does that mean? What is ensemble learning? Ensemble learning is when we take multiple different machine learning models, we combine them together to create a more powerful machine learning model. And what it does is that it adds a bit of, we generate like a couple of randomly generated decision trees based on our data set. We pick different K points in the data set. And then we can calculate like the decision tree for them. We combine them together to create a more powerful algorithm. So how is this done? Step 1 is to choose the number of trees you want to generate. Step 2, for each tree, randomly select K number of points with replacements. So in each tree, you can have like the same points. It doesn't matter, okay? And that's from our data set. And actually the program does it for us, so you don't have to do all that. Step 3 is to build each decision tree based on our K points. So we have like so many decision trees to work with. And step 4, for every new data point, make your n number of trees predict its category and cast its majority vote. Does anyone have any questions about this algorithm? Is anything confusing?
What's
Yeah.
the majority vote?
Majority vote, think about KNN, right? When you draw the line to n your K nearest neighbors, and you got like 4 oranges and 3 lemons, the majority vote would go to this. All right. If you have like n trees, let's say half of the majority of the trees pick oranges, but the minority picks apples. You would pick the majority. All right. And you can actually generalize this for multiple dimensions. All right. Let's code up random forest classification. Give me a second. I think for this one, because we feature scaled our X train and Y train and stuff like that, we need to re-implement it. Give me a second. We just have to redefine it. Reapply it. We have to re-implement it because we applied our scalar to it, and we don't want everything to be jumbled up and mixed up, because that would be bad. 80-20 split. So let's call this section random forest. Classification. From sklearn.ensemble. Import random forest. I can't type today. Classifier. Let's label this our classifier model. We basically do the same thing. Classifier equals random forest classifier. Oh, by the way, the reason why we're not doing decision trees is because why do one decision tree when we do multiple in random forest classifier? Random forest in general is more powerful than decision trees. Decision trees is actually an old method that's been completely outdated. I'm pretty sure no one these days uses just decision trees. It's all random forest classifier. Our n estimators equals, pick a number. 17 it is. All right. And the criterion, the methods we want to do the splits is by entropy. What entropy is, it's basically part of information theory. It's related to information gain. So I won't go too deep into it, just know that the criterion is called entropy. And finally, our random state is equal to 0. If you don't know what random state is, it basically makes it so that everybody in the room gets the same answer. If you didn't get the same answer, just raise your hand up. All right.
It also means that if you run the same thing twice, you get the same answer.
Yes, exactly. Yes. All right. So let me run these lines. Oops. There's nothing right there. All right. Now, we want to predict our values from our x-test. Comparing, predict, y. Let's call this y prep. The classifier. Wait, give me a second. Oh shoot, I forgot to do something. So sorry everybody. Go back. We forgot to train our model. Yeah, that's the consequences of popping off your laptop. Anyways, to train your model, you want to, it's the same thing. Classifier that fit, you want to train with your X train, as well as your Y train, all right? And then finally, we can do our prediction that was very bad. Something almost went really wrong, all right? Let's predict our X test. And now we do the same thing. We do the same concatenation thing. I want you guys to actually type it out so that it actually gets into your head instead of just copy and pasting. All right. Y pred. You want to reshape your Y pred by the length of your Y pred, so that's like how long it is and how wide it is. It's just one column. Then you do the same thing for the Y stuff. Reshape the length of your Y test. Let's see this. Perfect. As you can see here, the values are pretty good, if I say so myself. Yep. Maybe let's see if we can find a mistake. Oh, here's one. Here's a mistake. But that's fine, because we can actually evaluate using the same methods of confusion matrix. First of all, does anyone have any questions so far? No questions so far? Perfect. And finally, for model evaluation. Confusion matrix. Actually, I'll let you guys do it yourselves. I'll give you guys 5 minutes to do it yourselves, just for practice. And do not cheat. Do not scroll up and see what it is. So I want to test you guys, if you guys know how to evaluate your model. I'll give you guys 5 minutes to do it. And it's okay to search up on Google to search up like what a confusion matrix is, if you're still confused on that, and how to implement it in particular. get it? Yes. Oh, we're evaluating our model. Do you remember how we evaluate our model? Yes. Make sure you don't cheat because I want you to actually learn how to do it.
Anyone have any questions?
Anyone have any questions? Yes.
Yeah, the more the number of decision trees you have, the better.
The thing is, if you create more decision trees, in general, I think yes, right? Yeah, the more decision trees, the better. However, the issue is, you got to keep in mind the formula we've basically done. So the more decision trees you have, the worse it gets. Basically, scale, the worse in time complexity it gets. Okay? So we're basically scaling that exponential term by a constant, by how many decision trees are. Read that. I think someone else had a question. Yes. Yes, we are using the confusion matrix and the accuracy score. 2 minutes left before we resume.
So it's just slower with more decision.
Sorry?
It's just slower with more decision.
Yes, it's slower with
Is it more efficient?
One thing to note is that decision trees generally do have low accuracy than the other methods, so that's something to do.
Yeah, that's why we use random forest.
Random forests are generally the better.
Yeah, it accounts for the decision trees.
But does having more decision trees make it more accurate?
Yeah, it just makes it extremely slower, like I said.
But at the same time, you also have to have a threshold for overfitting, right?
I think everyone who hasn't finished the challenge yet. Oh, perfect. I guess we're done. All right then. Well, thank you for coming for classification. Thank you guys very much.